Hello everyone. Today, welcome back again to LFI Educates. Today we are going to continue with this third chapter, current electricity. And the topic that we are going to do today is Wheatstone bridge. Wheatstone bridge, when you say, it is just an arrangement of four resistors like this. One resistor. This is the second resistor. This is the third, and this is the fourth resistor. We write them as P, Q, R and S. These are the four resistors. In between these 2 points, C and D, suppose, we have connected one galvanometer. Galvanometer is an instrument used to detect small amounts of current, where current is passing or not to check. We use this instrument called galvanometer. Then we connect one key sometimes here, one key that we mark as K1, and then we connect it to this point D. These two other ends we connect to a cell. There will be positive terminal, the longer one, shorter one is negative. Then another key we can take here, let us say it as key K2. This arrangement, we call it as Wheatstone bridge. What do we do with this arrangement? Then these two are called, let me mark this as A, this point. In the arm AC, the resistor P, we call it as resistor P, and resistor Q, we call it as ratio arms. Suppose this point is B. This P by Q, we call it as ratio arms. This, in the branch AD, the resistor R, we call it as a known resistor. And then the unknown resistor, we write it as S, and with this arrangement, if we know the values of resistance P, Q, R, then this, in the fourth resistor, the resistance S, we can find out. Here what we do is, initially we allow the current to flow I in the circuit in this direction. Here, as there is a branch, it gets divided to I1 and I2. Then this current I1 flows and then again reaches this terminal C. It gets divided into two parts. One we call it as galvanometer current, we write it as IG, and the other one we write it as I1 became less by IG, so it will become I1 minus IG. Then it will come across this resistor Q, reach at point B. Then as soon as it comes and reaches B, this side you can see IG and I2 is coming and meeting here. So it will be I2 plus IG. These two currents, I2 plus IG and I1 minus IG, when it comes and meets here and joins together, then when you add them up, I1 minus IG plus I2 plus IG, then these two terms gets cancelled and I1 plus I2 will flow here, I1 plus I2, and the sum of these two, I1 plus I2, this I became I1 plus I2, we can call it as I as well, that is equal current I that will flow in the battery. So this way the current will flow. Now during the time of finding out the value of S, one condition you have to follow, that is called the balance condition of Wheatstone bridge. When no current flows through this galvanometer, that means when Ig is equal to 0, then the bridge is said to be balanced. The bridge is said to be balanced, and under that balanced state, this ratio P by Q will be always equal to R by S. R by S. And this Ig becomes 0 when the potential at point C and potential at point D both are equal. Then current won't flow. As we have discussed earlier, that charges flow from higher potential to lower potential. But if the potential difference is constant, both are same, they are same potential, then there will be no flow of charge. See here in the cell, potential here is more, here is less, this is current flows. But if these two are the same potential, then current cannot flow. So this is the balance condition of Wheatstone bridge. Suppose this is the ratio arm, this is the known resistance, then this unknown resistance S, you can find out R into Q divided by P. So knowing these three values R, Q and P, resistance S can be measured. This arrangement of 4 resistors, we call it as Wheatstone bridge. And the balance condition, again I repeat it once more, the bridge is said to be balanced if no current flows in this arm CD. That means if no current flows in this arm CD, the galvanometer will point 0 deflection. Galvanometer looks like this. There is a pointer, and in the middle it is 0, 1, 2, 3. Here 1, 2, 3 like this. In that case, under the balance condition, the galvanometer will be pointing straight up, indicating that these two are the same potential. Then the arrangement, we call it as balanced condition of Wheatstone bridge. Now let us prove this and see how do we get this ratio P by Q equal to R by S. Let us prove the balance condition of Wheatstone bridge. To prove the balance condition of Wheatstone bridge, you assume that current I is flowing through the cell in this direction from left to right. After reaching this branch, it will get distributed as I1 and I2. When the bridge is balanced, at these 2 points the potential is same, then the same current I1 will flow here and same current I2 also will flow. In that case, Ig will be 0. So if I write this as 0, then this will become I1, and here the current will be I2. So it will flow through CB as I1 and DB as I2. And when they combine together, I1 plus I2, then you will get I here. So you have sent current I with this cell, and then you got back again current I. It will complete the circuit. During this state, if you use Kirchhoff's second law, using Kirchhoff's second law, or you can say Kirchhoff's voltage law, KVL also you can write, in the loop ACDA, what you will get is the sum of EMFs is not there, there is no EMF here, so it will be 0. It's equal to the product of current and resistances. The product of current and resistance here is P. It is going the clockwise direction. Earlier also we took clockwise direction as positive, so here also I write positive I1P. Then when you come here, galvanometer is showing 0, the current is showing 0 here, so won't take this arm. Here we will come, when we come here, we can see that the current is in anti-clockwise direction. So anti-clockwise direction, we'll take it as negative, that is I2R. From here what we can get is I1P is equal to I2R. That will be equation number 1. The same way you can see in the next loop, that is CD, BC. Using Kirchhoff's second law in the loop CBDC, you can take in any direction, CBDC. And here also you can see that the sum of EMF is 0. So I'll start with 0 is equal to, here current I1 and Q is flowing this way. So it is clockwise. So I'll take positive I1Q, and then if I come here, I can see that it is going in anti-clockwise direction in this loop, like this. It is showing this side. That means it will go in the loop. Don't do this one. You see here, that is I2S. From here I can get I1Q is equal to I2S. I'll mark this equation number 2. On dividing this equation 1 and 2, on dividing equation 1 and 2, what I'll get is I1P by I1Q is equal to I2R by I2S. I1, I2, if you cancel it, you'll get P by Q is equal to R by S. This is the balance condition of Wheatstone bridge. But when you are writing it, please mention about the flow of current, and in balance condition, of the bridge, or in balance condition, Ig must be equal to 0. This you have to remember. Let us solve this question. The Wheatstone bridge circuit has the resistances in various arms as shown. This P, Q, R and S. Calculate the current through the galvanometer. You have to find the current through the galvanometer. In this case, the Wheatstone bridge is not balanced. So you cannot take P by Q equal to R by S. Then you won't get the value of Ig. So what we have to do is, using Kirchhoff's rules, you'll have to find out the value of Ig. So let us take the loop one by one. Here A, B, D, A. I used to take using Kirchhoff's voltage law in the loop A, B, D, A. The product of current and resistance, let us take first. It is in clockwise direction showing. So it will be positive 100 I1, 100 I1. Then this way it is coming like this. It's still clockwise. 15 resistance in the galvanometer is 15 ohm. So Ig 15 Ig. This is also plus 15 Ig. And then this resistor, the current is coming this way. So it is showing anti-clockwise. So it will be negative 60 I2 minus 60 I2 is equal to sum of EMF. There is no EMF here in this loop, so it will be 0. Let us mark this equation number 1. Likewise, we can choose this second loop. In the loop BCDB, using Kirchhoff's voltage rule again, let us take from here. This is showing clockwise. So 10 times I1 minus Ig, 10 times I1 minus Ig. Then this one is showing anti-clockwise, so minus. It will be 5 times minus 5 times I2 plus Ig. Then this one, it is showing anti-clockwise, so minus 15 Ig, minus 15 Ig is equal to sum of EMF. Here also it is 0. There is no EMF, so I am writing here as 0. Let us open the bracket. 10 I1 minus 10 Ig minus 5 I2 minus 5 Ig minus 15 Ig is equal to 0. So here 10 I1, there is only one I1, 10 I1. Then Ig you have 1, 2, 3. Minus 15 minus 5 is minus 20. minus 20 minus 10 is minus 30 Ig. Then minus 5 I2 is equal to 0. Let us mark this equation number 2. In both the equation, if you look carefully, you have I1, I2, Ig. Here also I1, I2, Ig. 3 variables are there. So what we'll do is, we cannot solve this 2 to get the value of Ig. So what we'll do is, we'll take the third circuit, this way we'll take it. This is also one loop. You can see it's a closed path. So in the loop, A, B, C, E, A. Again we'll use Kirchhoff's voltage law. This is showing like this, so it's clockwise, so positive 60 I2, 60 I2. Then this one is also showing this way, so positive. So I2 plus Ig into 5. So it will be plus 5 times I2 plus Ig is equal to, there is no more resistances. So here you have your EMF. So this is the positive terminal. We know that current flows from positive to negative. So this is also clockwise. So we'll take it as plus 10. Then here what we get is 65 I2 plus 5 Ig is equal to 10. We mark this as equation number 3. But with this, we will find out the value of Ig first. After finding out the value of Ig in terms of I2, we will put in equation 1 and 2. Let's see what happens. We will get equations for I1 and I2, and after that we can solve. So this one, if I write 5 Ig equal to 10 minus 65 I2. 10 minus 65 I2. Or like this structure, do you have? You can check it. 65 I2. Like that is not there. 65 I2. So this is the way that we have to do. Ig is equal to 10 minus 65 I2 divided by 5. So this one you can write it as Ig is equal to 5. You can take common. 5 2 times is 10 minus 5 13 times is 65. This is Ig divided by 5. This 5 we can cancel. So Ig is equal to 2 minus 13 Ig. Sorry, this is I2. This is I2. So this one we mark it as equation number 3. Now we'll put the value of Ig in equation 1 and equation 2. Now putting the value of Ig from equation 3 in equation 1 and 2. Let us see. We put the value of Ig. Here you have equation 1. So you put the value of Ig in equation 1, then it will look like this. 100 I1 plus 15 times Ig is 2 minus 13 I2 minus 60 I2 is equal to 0. So it will be 100 I1 plus 30 minus 15 into 13. 5 3s are 15. 3 4 5 1 5 9 1 195 I2 minus 60 I2 is equal to 0. So here what we get is 100 I1 minus, if we add them up, both are minus minus, 5 15 5 1 in minus 255 I2 is equal to minus 30. This constant term we can bring here. Then we can reduce the equation dividing by 5. If you divide it by 5, you will get 20I1 minus 5 also 25, 5 also 5, I2 is equal to 5, 6 are 30. This one will take as equation number 4. Now, we'll put in equation number 2 as well. Then I1 minus 30Ig minus 5I2 is equal to 0. So here also we'll put in the value of Ig. Then you will get like this: 10I1 minus 30, Ig is 2 minus 13I2 minus 5I2 is equal to 0. So we'll open the bracket. 10I1 minus 3 to 6, 60. Then minus to minus is plus. 13 to 13, 390. I2 minus 5I2 is equal to 0. So 10I1, then I2 plus minus 5 if you do, will be plus 385 I2 is equal to minus 60 will become plus 60. Here also you can divide by 5. 5 2s are 10, I1 plus 5 7s are 35. 3 5 5 7s are 35. I2 is equal to 5 1s are 5, 5 2s are 10. This one we can mark it as equation number 5. Now on solving equation number 4 and 5, you will get the values of I1 and I2. Now let us solve these two equations, equation 4 and 5. We can check the coefficients 2 and 20. 20 and 2. 2 tens are 20, 2 ones are 2. So with 1 we will multiply equation number 4. 1 into equation 4. It will give us the same thing. 20 I1 minus 51 I2 is equal to minus 6. And then with 10 we multiply equation number 5. 10 into equation 5. 10 2s are 20 I1 plus 77 into 10 is 770 I2 equal to 10 into 12 is 120. Then you can subtract it. While subtracting these two, plus 20 minus 20 will get cancelled. Minus 51 minus 770. 770 minus 51. Both minus, you have to add it. You have 2 1 in hand. 8 minus 812. 821. I2 is equal to minus 126. Minus minus you can cancel it. Then 126 by 821. Putting the value of I2 in equation 3. Here is equation 3. That is Ig is equal to 2 minus 13 I2. 2 minus 13 I2 is 126 divided by 821. So if you do like this, 126 into 13, or you can cancel this. 13 into 7, 21, 7, 7, 8, 9. Now it won't come. So this one you can multiply. 126 into 13, 6 2 is 18, 6 7, 3 1 is 3, 6 2 1, 8, 13 3, 1 in hand, 6 1, 1 6 3 8 divided by 821. So LCM if you take 821. Multiply 2 times 821 into 2, 2, 4, 8 2 sir, 16. So it is 1642 minus 1638. So it will give us 1638 if you subtract it. 4 by 821. Then you write here ampere. So like this you can get the value of Ig. So let us solve this question. The figure shows two circuits, each having a galvanometer and a battery of 3 volt. When the galvanometer in each arrangement do not show any deflection, obtain the ratio R1 by R2. Let us take the first case. The galvanometer does not show deflection, so it's an arrangement of Wheatstone bridge. You can see very clearly, and there is no current flowing to the galvanometer. So solution when we do for the first case, let us mark this as number 1. So we can redraw the diagram as well. Like this you can do first, then you can put the resistors. This is 6 ohm, 4 ohm, R1, 9 ohm, and galvanometer is here. Then this is your 3-volt battery, and like this you can do. Then when galvanometer shows no deflection, then P by Q is equal to R by S. You know this one, the balance condition. 4 by R1 is equal to 6 by 9. 3 2s are 6, 3 3s are 9. So 2R1 is equal to 4 3s are 12. So R1 you can find out 12 divided by 2 is 6 ohm. So this is the first case. But when you look at the second case, the diagram is somewhat like this. Here is given 6 ohm, this is 12 ohm. There is one battery here. In place of galvanometer, they have placed one battery. This is 3 volt. Then this is your galvanometer, and the resistance of the galvanometer is given as 1.20 ohm. Like this it is given to you. So what we'll have to do is we'll have to draw the equivalent circuit. Cell, you can see from cell it goes to 12 ohm and 6 ohm. From the cell it goes to 12 ohm and 6 ohm. Like this also you can do, and leaves the current through this terminal, this end, right side. Here it leaves from 8 and R2. 8 and R2. So top 12, 6. Then here will be 8 and R2. Here will be 8 ohm and R2. So it leaves towards the cell. 8 and R2, 8 and R2 it leaves towards the cell negative terminal. So like this you can draw the equivalent circuit. After you draw the equivalent circuit, then you can use the balance state of Wheatstone bridge here also. In this case, the galvanometer will become exactly like before, 60 ohm, and the battery will be of same 3 volts. So when you do the balance state, you write 12 by 8 is equal to 6 by R2. 4 2s are 8, 4 3s are 12. 3 R2 is equal to 6 2s are 12. R2 is equal to 12 divided by 3. 3 4 times is 12, so it will be 4 ohm. Like this you can find out R2, and then you find out the ratio R1 by R2. Therefore R1 by R2 is equal to R1 you got 6 ohm, R2 you got 4 ohm. So 2 2s are 4, 2 3s are 6. So R1 is to R2 is equal to 3 is to 2. This way you can find out the ratio. This question came one year in CBSE, so you need to know. The next topic that we are going to learn is meter bridge. Meter bridge is a practical form of Wheatstone bridge. It is also known as slide wire bridge. A meter bridge looks somewhat like this. These are steel stripes on a wooden board, and 1 meter scale will be provided here. Markings will be there starting from 0 up to 100 centimeter. It will be equal to 1 meter. The scale will be provided. Now, just at these 2 terminals, you will get 1 wire made up of manganese or Constantan alloys. Earlier we said that alloys, they offer very less resistance. This is the wire. This arrangement will be done on a piece of wood, and this instrument we call it as meter bridge. Here you can find 2 gaps. In one of the gap, you will put 1 known resistance or a known resistor. Let us say it is R, and in this gap we will put 1 unknown resistance that we want to find out. Let us say it as S. This resistance of this resistor we want to find out. Then there is a galvanometer that we have to connect at this point. This is a galvanometer, and then at the end of the galvanometer 1 more wire will go like this, and this end we call it as jockey. Now this arrangement, you connect it this way. An auxiliary circuit will draw, 1 cell you will take it, or a battery you will take it, then 1 key you will take, and then connect at these 2 ends. When current flows through the cell, it comes here in the anti-clockwise direction as soon as you give the switch. So how it works, what is the principle that we have to know now? The principle of meter bridge is the balanced condition of Wheatstone bridge. Earlier we learned the balanced condition of Wheatstone bridge is P by Q is equal to R by S. So this is the balanced condition of Wheatstone bridge, and we said that S is the unknown resistance, and this is the ratio term. These 3 resistances, if you know, then you can find out the 4th resistance, that is S. And here S is the unknown resistance we are going to find out. Then what you will have to do is, first you will close the path, switch on, allow the current to flow, and then this jockey you will have to ride on top of the wire. When you ride on top of the wire, at some certain point, say at this point, when you are touching the wire, then suppose the galvanometer is showing no deflection. When the galvanometer does not show any deflection, then we know that the bridge is balanced. This part, suppose this is a jockey, this part we call it as length L of the wire, we will treat it as P, and the other end, that is 100 minus L. These are in centimeters. We are taking it in centimeter, the unit. Then this part we assume it as Q. So this arrangement, if you look very carefully, it is similar to that of our Wheatstone bridge. Here P by Q is equal to R by S. In the balanced condition, P by Q will be equal to R by S. Now P by Q. Now P by Q, the ratio arm, as resistance is directly proportional to the length of the conductor, we replace P with L and Q we replace with 100 minus L. So P gets converted to L, Q gets converted to 100 minus L, and this is your known resistance R, and this is your unknown resistance. So S will be equal to R into 100 minus L divided by L. By putting the values of R, the known resistance, the length L, how much centimeter it is, and this also length L, we come to know about the unknown resistance, that is S. This is how it works. So three things you have to know. What is meter bridge? Then first of all you have to know that it is a practical form of Wheatstone bridge. It is a practical form of Wheatstone bridge. And what is its principle? Then its principle of working is the balanced condition of Wheatstone bridge. When the bridge is balanced, then only we can use this relation P by Q equal to R by S. And thirdly, for what do we use meter bridge? Then to measure an unknown resistance. S is the unknown resistance. Sometimes two resistance, both you don't know. Suppose R also you don't know, S also you don't know. Now in that case, you can find the ratio of the resistance as well. That is the second application of meter bridge. You can look here very carefully. L and 100 minus L, if you know, if you put the values, suppose say R by S I want to find out, then it is L by 100 minus L. L, suppose here it is around 20 centimeter. 20 centimeter. Then the remaining 100 minus L will be 80 centimeter. Then you can find out the ratio as well. 2 ones are 2, 2 fours are 8, so it is 1 is to 4. Let us see this very interesting question. In the meter bridge experiment, balance point was observed at J. Balance point was observed at J with AJ equal to L. If AJ is equal to L, then JB will be 100 minus L, that we know. We take in terms of centimeter. The values of R and X were doubled and then interchanged. The places were interchanged. What would be the new position of balance point? Now to solve it, the first one, in a balance condition, we know that L by 100 minus L, without interchanging, without doubling it, let us see the balance condition. L by 100 minus L, P by Q equal to R by X is equal to R by X. In this state, the balance point is L. Balance point is L. Now as you are going to interchange X and L, then it will become X by L, X by R, then it will become here 100 minus L divided by L. Then you are doubling it, 2 times of it you are doing. Then 2 will get cancelled, double to that if you do, and exchanging it, then it will be 100 minus L by L. So if you exchange this polarity, the balancing point also will exchange. It will become 100 minus L. When X and R are interchanged, R and X were double and interchanged. When R and X are doubled and interchanged, then we can see that the balance point will become 100 minus L. The balance point will be 100 minus L. this should be your answer. Then the second case, you can see if the galvanometer and battery are interchanged at the balance point, how will the balance point get affected? In meter bridge, when it is already balanced, then at that time if you take out the cell and put it in place of galvanometer, and galvanometer if you place it in the position of the cell, there will be no change. It will remain unaffected. So you write the answer like this. The second one, I'll write down here. When the battery and galvanometer are interchanged at the balance point, if the galvanometer and the cell or the battery are interchanged, it will remain unaffected. The balance point will remain unaffected. So like this, you will solve the question when meter bridge question comes. Thank you and have a nice day. Stay tuned with LFI Educates.